In this video, we are going to go over the paper called Deep Learning on a Data Diet, Finding Important Examples Early in Training. A paper resulting from a collaboration between the Stanford University, Facebook AI, and Element AI. When it comes to deep learning, a natural question is, how much of the data is redundant? And what examples are more important for generalization? And more importantly, how do we find them? And these questions are what this work is specifically about. Here is the main finding of this article. Let's read it. We make the striking observation that on a standard vision benchmarks, the initial loss gradient norm of individual training examples averaged over several weight initializations can be used to identify a smaller set of training data that is important for generalization. What this says is basically this. If you have a deep learning model F, and if you pass an observation xi to it, and essentially use its label to compute a loss, if you compute this derivative of loss with respect to the parameters, and this W is the entire parameter of the network, and if you take the L2 norm of the flattened version of this, and if you basically randomly initialize this F of yours, with different initialization weights 10 times, and then compute this, you will have a somehow model agnostic view of the gradient direction and the magnitude of gradient direction for each one of the items. And this magnitude of gradient direction can be used as a metric regarding indicating how important examples are for training and specifically for generalization performance. Now this thing is relatively expensive to compute, therefore they have another proposal as well, which is this. After only a few epochs of training, the information in gradient norms is reflected in the normed error L2 distance between the predicted probabilities and one-hot labels, which can be used to prune a significant fraction of dataset without sacrificing test accuracy. Meaning that you can also do some early training and then use this, which in this case P is the softmax probabilities, and this, as you can see, is the norm of the derivative of loss or gradient of loss with respect to logits or logit gradient. This can be used in lieu of this. Now with these observations, they propose a data pruning method that uses only local information early in the training, and also talk about the impacts on the training dynamics. The introduction talks about advancements in deep learning and the related works, and mainly the motivations behind this work, and it poses important questions to be answered, including 1. The examples that are somehow redundant, what exactly makes them redundant? How early we can recognize such examples without spending too much time on repeated long training sequences? How many examples do we need to remove? And how does it reflect, how is it reflected in the data distribution? And the answers to such questions have a lot of applications, such as reducing training time and optimizing memory requirements, and additionally providing better insight as to what the network learns and how it does that. The puzzling result that they report is that if you focus on the norm of the loss gradient for each item, for each one of the individual examples, you can use it to identify important examples. Now, if you focus on only one trajectory, a single trajectory, it's not going to be great. But you can perform multiple weight initializations and compute these norms for these individual items and then basically average them over these multiple weight initializations and then use the result as a score to rank the examples. And as empirical results, they, for example, show that they can prune 50% of examples in Cypher 10 without affecting the accuracy at all, and 25% of examples in Cypher 100 can also be pruned with only 1% drop in the accuracy. Again, emphasizing that there are examples that are not really influential in the generalization performance and can be removed. So here are the main contributions of the paper. If you pick training examples xi, yi's, xi being the observation, yi being the label, one can compute the expected loss gradient norm, they call it grand score, and this can help with better understanding of the bounds of the expected change in loss for a single arbitrary example when you remove the xi, yi from the training set. They show that you can use these grand scores at initialization and basically prune the training examples that have small values for that. And if you do this on Cypher, you can remove 50% of the data without actually losing any accuracy. Now, given that that one is expensive to compute because you need to have the access to all the gradients of all the parameters and compute the norm, They show that with a few epochs of training, namely something like 20 epochs on Cypher, you can approximate this grand score by the norm of the error vector, which is also the gradient of loss with respect to the logits, and they called it the Deltoon score. Then they studied the rows of examples that have the highest Deltoon scores and show that sometimes removing the very highest scoring examples can provide a boost in performance, especially true for the cases of corrupted label regime. They also provide some analysis based on linearly connected modes and the concepts of neural tangent kernels to better understand the relationship between these types of properties and the training dynamics. Here are the notations used in this paper. S, composed of the tuples xi, yi, and we have n tuples like that, are the training set, which includes the example observations that are used in the training sequence, along with their labels yi's. The input vectors, or the observation vectors, are d-dimensional x's, and they come with the one-hot vectors y, which basically indicate to which one of the k classes the example x belongs to. Then the neural network architecture with weights w is shown as fw of x, and it outputs the k-dimensional logits with d weights. So w is the flattened vector of network parameters, and it's basically d-dimensional. And sigma is the softmax function defined like this, and p, parameterized by the parameters w and x, indicates the softmax function applied on these logits and therefore the predicted probability vector p hat. And then this sum over here indicates the cross entropy loss. Now, if you consider a parameter set w, we have w0, w1, w2, all the way to wt, indicating the iterations of a stochastic gradient descent, meaning that if you consider the mini batches S0, S1, all the way to St minus 1, indicating t iterations, the rule for updating this parameter set is like this based on the stochastic gradient descent. Meaning that you have an eta, and then you have a bunch of batches, you sum the gt minus 1, basically the gradient of loss with respect to the parameters, and you use the gradient descent rule with this learning rate coefficient eta over here to use the gradient descent and optimize these parameters. The definition of grand score is like this. So high t xy, which is the grand score of the training example x and y at time step t, is defined as this. So consider gt of x and y. G is the gradient of loss with respect to the parameters at time t. And now this EWT here is being, so basically you're taking this norm and you are trying to find the expected value over different instantiations of random variable WT. Experimentally, what this means is that you want to initialize your network with different weights, and then for each example x and y, compute this value, and then by taking the average, reach the score high t x and y. Another important quantity is the instantaneous rate of change in the loss on an example xy at time t, where the gradient is computed on the minibatch st. So using the chain rule, you can see that this value here defined as the instantaneous rate of change in loss is going to be equal to the gradient of loss with respect to parameters times the gradient of parameters with respect to time, where this dwt dt is approximated with wt plus 1 minus wt, which based on the updating rule in the gradient descent is this. The reason why it is important is because we want to analyze if you remove a training point from the minibatch st, how does it affect this delta t? Related to this is lemma 2.2, which is very important. Consider the training set S, which includes all the examples that are used in training the model. Now let's define S not J as a training set without a specific example. Now if you consider all the other examples xy, there is going to exist a C, which is a constant, a scalar, which helps bounding this, which helps defining this upper bound. Now, delta was again the instantaneous rate of change in loss on an example at time t. And you would also have, so you have the minibatch st as well. Now, you consider S, and you consider S without the example, without the jth example. And now the idea of this term here is that you want to see how much does the instantaneous rate of change in an example would change if you remove a certain example from the training set. So to show that, you could use chain rule on the definition of delta txy, and you would get this. Now weights are updated according to the stochastic gradient descent rule. Therefore, you know that dwt dt is this summation over here. Now by defining C as this, you can essentially show this lemma. This states that the contribution of a training sample, xy, to the decrease of loss at any other example is bounded by this equation. Now if you consider the example that you want to remove, for example in this case the example xjyj, this term does not depend on it, which means the thing that remains in this upper bound that depends on it is this gradient norm, which again signifies the importance of the gradient norm for the individual training examples as a measure for selecting them. Now remember that f of x would give you the logits, and if you consider the kth logit, you could have this, and you can compute the gradient with respect to the parameters, and let's define it as psi t kx. And again, x is an input observation. Now, if you look at the grand score using the chain rule, you can essentially write it like this. Now, with this kind of equation, you also know that the gradient of loss with respect to the logits is this. Now, given this condition, if you look at these psi's, and if they are roughly orthogonal across logits, and if they are of similar size, these would pave the way for approximating the grand score by the norm of the error vector, which is called L2, and defined like this. In comparing these with the forgetting event defined before, which is basically a forgetting event is the point in the training where a classifier makes a correct classification and into an incorrect one. In other words, forgets how to classify an example correctly. And the number of times it happens throughout the training can comprise a score called the forgetting score. It was shown before that the examples with low forgetting score can be completely omitted during training without any noticeable effect on the accuracy. Now, in the definition of grand score, and basically trying to relate that to the L-tune, given that psi t's are time dependent, it makes it complicated to analyze across multiple steps. So a simplifying assumption is to remove this time dependency of psi t, and also makes it sort of uniform across the different logits, which will lead to this norm on the grand score. Now, if you take two examples of xy and x prime y prime, where they have a similarly sized size, the example that is learned faster is going to have a smaller grand score on the average throughout training as well. Also noting that this error vector, if properly scared, the norm of it is going to be an upper bound on the 0-1 loss, and therefore can also limit the number of forgetting events as well, meaning that it also relates the high number of forgetting events with a high value for grand score. Now, the main empirical analysis in this work has been done using ResNet 18 and ResNet 50 on 3 datasets of CIFAR 1000 and Cynic 10. The averaging over different initializations has been done using 10 independent trainings. They retrain networks from random initializations only on the selected subset. Now, this picture shows many of the important results in this paper. So, the columns, the first one is CIFAR 10, the second one is Cynic 10, and the third one is CIFAR 100, which is a more complicated dataset. And on the left, on the y-axis, you will have a final test accuracy. Now, let's look at the first row. In the first row, we want to show this impact of the epoch at which you compute the scores. So we know that these scores are computed throughout early training. So this early training can be up to 20 epochs, and it shows the impact of choosing the score at each one of these epochs throughout 0 to 20. You can see that for the grand score, the initialization result is actually good, meaning that just averaging the initial gradient over multiple different randomly initialized set of parameters can lead to a good score for pruning. And epoch 20 seems to also be a good choice for the L-tune score and for forgetting. Note that the purple line here is no pruning, and the pruned randomly with the red line here are the two baselines that we are comparing these against. And on the bottom row, you can see that on the x-axis you have the fraction of the dataset pruned, and So basically you have 90% of the data all the way until somewhere like 45% of the data remaining. And you can see that the L-tune and the forgetting score seem to be very good for most of these. Now let's read some of the important points that the paper mentions. The first one is about pruning at initialization, which shows the impact of grand score. But for L-tune score, some early training is needed, and it cannot be used right off the bat after initialization. With some early training, L-tunes can be quite competitive and be a great score for pruning. Another important thing that they mention is that when you want to have a very, very small ratio of examples kept, in other words, in extreme levels of pruning the dataset, with either using L-tune or grand, there is going to be a sharp drop in the performance. And they hypothesize that it is because focusing on only the highest scoring examples based on L-tune or grand is going to lead to a bad coverage of data distribution. Namely, saying that L-tune is somehow a proxy for the significance in terms of difficulty, focusing on them when you have a very, very high pruning rate means that some classes might be underrepresented, and therefore you encounter a case in which you're fitting a small number of very difficult examples and do not keep a variety of examples for training models with good test error. They also do experiments such as, for example, changing ResNet 18 to ResNet 50 and showing that even with a lot more parameters, it's going to kind of exhibit the same amount of same performance trajectories, indicating that this type of gradient-based analysis and scoring has to do with the property of the data itself and not with the model, so therefore it's some sort of a model-agnostic way. They also show that when you consider label noise, so in here, in this figure, you have this fraction offset. So what this means is that in these two figures, in the left one, you have no label noise. In the right one, you have 10% label noise. And what happens here is that you want to pick 40% of the examples from this cipher 10. You sort the examples based on ascending L-tune score. And for example, for the offset of 0, you pick the bottom 40%, and at 0.6 you pick the highest scoring 40%. So you do this thing, and it shows that the peak and this drop is going to kind of be shift to the left as you do this randomization, because it has an impact and has a considerable impact on the gradient. Therefore, the strategy of always picking the highest scoring examples based on L-tune is not optimal, especially when you have corrupt labels. Another thing they have done is looking into the analysis of this approach using the neural tangent kernel idea. They know that when there is not an infinite width setting, the NTK is going to evolve with high velocity in the initial phase of the training. And then the NTK velocity stabilizes at a smaller value and then remains nearly constant for the rest of the high learning rate phase of the training. They show that if you consider the kernel velocity, the highest scoring examples in the case of label noise, for them the kernel velocity is going to actually drop, as you can see in this figure right here. And they conjecture that while the kernel velocity is higher for harder examples that the model is actively trying to fit, the kernel velocity drops off for the very highest scoring because maybe they are too difficult to learn, or perhaps because they are unrepresentative samples, or because they have label noise. Next, they focus on the linear mode connectivity and the geometry of the loss surface. The idea of linear mode connectivity is as follows. You consider W1, W2 up until WT to be a training trajectory for a parent network. And then you also fix a spawning time T star. And you create an independent training trajectory, VT star plus 1, all the way until VT. And this is computed using different independent mini batches. But starting at VT star, therefore the initialization is conditioned. So this V is child network, and this is the child trajectory. Now, the error barrier between two weights W and W prime is defined like this, which is the maximum deviation of training error surface above the line connecting the empirical risk. Now, the concept of mean training error barrier spawning at time T star is defined like this, with the onset of a linear mode connectivity being the earliest T star at which point this barrier becomes 0. Now, going back up to this picture, you have the minimal tunes, maximum tunes, and random. And you can see that for the minimum one, this error barrier actually goes to 0 quite faster than the maximum ones. So in terms of loss surface, these two subsets, meaning higher tune and lower tune, behave differently. The work then talks about the articles that were related to it and the different approaches, which are quite interesting to read. Now they use jacks and flags in their implementation. And here are their hyperparameters: learning rate of 0.1, Nesterov momentum of 0.9, weight decay of 5e minus 4, and a batch size of 128 for Cyphars and 256 for Cynic. Their scores are computed using the early training over 10 independent runs. This figure shows the Spearman rank correlation between grand scores obtained by a given number of independent runs, shown on the x-axis here, and the one using 10 independent runs, and also showing its impact on accuracy as well. Regarding the kernel velocity experiments, this is a definition of the kernel velocity. Regarding the correlation between different scores, they also show that there's a good correlation between L2 and forgetting scores, which they also showed by the theoretical justifications as well. They've also shown that adding label noise is going to significantly change the distribution as well. And this concludes our discussion of the paper called Deep Learning on Data Diet.